This week has been about optimization, finding a local max and a local minimum. And we're just taking the stuff that we did in Calc 1 and modifying it to fit a function of two variables. Our old plan was to find the critical points was take the derivative, set it equal to 0, and solve. Also find out where the first derivative was going to be undefined, but primarily take the first derivative, set it equal to 0, and solve. We do the same thing with a function of two variables or even more variables. We just end up with a system of equations. We take both the first derivatives, set them equal to 0, and solve. It produces a system of equations in x and y, but we're doing the same thing. We can also think of it as solving a vector equation where the gradient is equal to 0. We're looking for places where the gradient is equal to 0, because that's the same thing as fx equaling 0 and fy equaling 0. Take the first derivative, set it equal to 0, and solve. Next, we want to classify each critical point as a local maximum, a local minimum, or a saddle point. In the single variable times, we had multiple ways to do this. One of the ways was to look at the concavity with the second derivative. Take the second derivative, plug in the critical points. If the second derivative was positive, then we have a local minimum. If the second derivative was negative, then we have a local maximum. If the second derivative was also equal to 0, then we're in kind of a fishy territory. Not necessarily a saddle point. It might just be that the function is exceptionally flat at that point. Think about the difference between x cubed and x to the fourth. X cubed has a second derivative equal to 0 and a first derivative equal to 0 at 0, but neither a minimum nor a maximum. That's a saddle point on x cubed. But x to the fourth does have a minimum, a local minimum at 0. And the second derivative is equal to 0. So you can't tell if the second derivative is equal to 0. Now that we have a function of two variables, we have four second partial derivatives. So we had to find a way to combine all four second partial derivatives. And we did that through the determinant of the Hessian matrix, fxx times fyy minus fxy squared. A quick note, the mixed partials fxx and fxy and fyx are going to be equal. So this fxy squared is really fxy times fyx, but the mixed partials are equal. We see some similar things in the second derivative test that we had before. If our determinant of the Hessian matrix is equal to 0, then our second derivative test is inconclusive, just like it was before. The second derivative test, we just had to plug critical points into the second derivative, positive or negative. If they came out 0, our test is inconclusive and we had to do something else. And the same thing is true here with our second derivative test for functions of two variables. If our determinant of the Hessian matrix is 0, then the second derivative test is inconclusive. Then there's a little bit strange structure. If this D is positive, then we only have to look at fxx. We don't have to look at both fxx and fxy. We just look at fxx. And if D is negative, we don't have to look at anything else. We just immediately get to conclude saddle point. So this is what we want to talk about today. We have raised the question, why do we only care about fxx? What about fyy? So fxx being positive kind of suggests concave up in the x direction, Why are we not concerned about what's going on in the y direction? So that's what I want to think about here. Why do we only care about one? The thinking is going to go like this. Remember, it's the same thinking that we had in functions of one variable. Second derivative positive suggests a local minimum. When we look at fxx, the derivative in the second derivative, both in the x direction, this is suggesting that the function is concave up in the x direction. Fxx positive now this is super fishy. And I can hear the mathematicians typing in comments already. But that's only because they didn't notice that I had turned comments off. So quiet you. So I'll do this. Calm down, mathematicians. This is how we think about things. So take your rigor elsewhere. Rigor can show up in all kinds of places. Not here. We're just thinking about it. We are kind of thinking about concavity in the x direction, just in the x direction. Since the second derivative is positive, that suggests that as we're going along in the x direction, it's bottoming out. We have concave up. It's a little bit weird to say it this way because we have other things going around. Because we have x's and we have changes in y. But fxx positive suggests that f is concave up in the x direction. Actually, this whole thing is fishy, so I'm going to put quotes around this whole thing, concave up in the x direction. No, depends on the situation. Scalars distribute over vector addition. So why are we not worried about fyy? So aren't we worried about what's going on in the fyy direction? How do we know that fyy is also positive? Because if I look at fxx and say it's positive, I immediately jump to local minimum. I just didn't pass go, didn't collect $200, went right to concluding it's a local minimum. I didn't bother checking to see if the function was concave up in the y direction. How do we know that fyy is positive? D is positive, fxx is positive. We know that fyy is positive. Why is that? I like this because we're all thinking about it. We don't need to think about it. We need to calculate about it. This is a straight up calculation question. Exactly. If it was negative, then if fyy was negative, then D would have been negative because look at the calculation. D is fxx times fyy minus fxy squared. We're subtracting something positive. If we get a positive value for D, fxx and fyy must have the same sign. That's why we don't have to look at both. We've already looked at both here. If D is positive, then fxx and fyy must have the same sign. Because D ends up being positive, and this is after we subtracted something that is most definitely positive. fxy being squared, we're subtracting some positive amounts from the product fxx times fyy. That means we must have started positive. So that's how we know that once fxx is positive and d is positive, that allows us to, d being positive, allows us to conclude fxx and fyy have the same sign, so we only need to look at one of them. We could rephrase this whole thing as d positive and fyy also positive. I'm sure there's some alternate universe where there's some other version of Professor Leach that's like, oh, I'm sure there's some alternate universe where some other Professor Leach is like, oh, they're just looking at fxx while we look at fyy. And then in some other alternate universe, there's some much more ambitious version of Professor Leach who's traveling through all the multiverse, eliminating all the other Professor Leaches so he could become more powerful. Yeah. The Jet Li movie? There's a Jet Li movie where Jet Li can somehow travel between all these different multiverses. I don't know if they call them multiverses. And then he would kick his own ass so that he could absorb their power, because there are fewer Jet Lis to spread out all the martial arts prowess. Oh, Doctor Strange, they actually call out the multiverse. But I have not seen Everything Everywhere All at Once. Everybody tells me I have to see that. So yeah, I do want to see that. The fact that I'm still here either indicates that I'm just not very powerful, or there's definitely not a leech like running around the multiverse assassinating other Professor Leeches to gain more power. Oh, maybe that's it. It's like a Heisenberg thing. I don't know. I think I know myself pretty well, and that sounds like a lot of effort for what? Right? Is he like, maybe there's like some Professor Leach that did this for a little while, and now he is like the ultimate math teacher. And so he's not like good at fighting, because I've never been good at fighting, but he's like the ultimate math teacher. And that's why he went through and collected all his power. I don't know. Or like there's the multiverse where it's like there's other versions of other choices that you made, right? So somewhere out there, there's a multiverse where instead of going to school for math, because that was fun, it's like, oh, no, I think I will give professional musician a shot. And then there's some leech out there just like still living at home, not playing gigs because it's not very good, a musician. And it's like right there. So I think about this a lot. So anyway. So we move on to this next one. If D is negative, then we get a saddle point. If D is negative, notice that we start off with fxx and fyy. That kind of indicates that fxx and fyy have opposite signs. It could be that they have the same sign and fxy is just huge. But the main thing that we get from this is if D comes out negative, this is an indication that fxx and fyy have opposite signs. Probably. We're using this to think about the problem, not for sure just to calculate everything. So get off my back with your pedantic actually. Don't at me. This is a strong indication that fxx and fyy have opposite signs. So we've got a point, a critical point, where in the x direction, concave up, and the y direction, concave down. Different concavities in each direction. So imagine in the x direction, fxx is positive, and imagine in the y direction, fyy is negative. So in the x direction, draw something concave up, and in the y direction, draw something concave down. And that's creating this saddle point. I can't draw it, but every semester I try. So in one direction, we've got a concave up. And in another direction, we have some concave down. Yes. If we have concave up in one direction and concave down in the other, then our second derivatives at those points will have opposite signs, making sure that D will come out negative. And if D equals 0, we don't get to draw a conclusion. We have to do something else with our function. Just like in single variable calculus. If our second derivative came out negative, we had to appeal to something else to figure out if the function was bottoming out, topping off, or just going flat, taking a rest, and then continuing whatever it was doing before. I love the parallels with the old classes. That's why Calc 3 is the easiest calculus, because it's the same thinking as Calc 1 and Calc 2. We're just adapting it to more variables. Any questions? How's everybody okay? This is the optimization game. We want to find the maximum and minimum values of a function. And we're doing essentially the same thing that we did in Calc 1. It's just kind of like more detail. The next place we want to go is constrained optimization. So when I looked at this, when we looked at our function from before, it was just a polynomial function that was defined everywhere. So when we were looking at, that's why we were looking for a local minimum or a local maximum. It might not be the lowest points on the entire graph or on the entire surface, but it's the lowest point in some local area. All of a sudden, I can't remember the highest peak in California. What's the highest peak in California? Probably. Doesn't matter. So let's go the other direction. So if we go to Death Valley, that's going to be like the lowest elevation in California, right? That's the lowest place in California, I think. Is it below sea level? You know what? This level of the room that I'm standing in is the lowest point in this classroom. So here is, this is locally a low point. But and sitting in the back row of this classroom, locally, that's the highest point in this classroom. So if you're sitting in the back row, you are at a local maximum, but you are not at the highest point in the building, or on the campus, or in the state, or on the earth. Or, well, let's stop at the earth for globally, because it's like a globe. So there are higher points, but locally, that's the highest point in this area. Now, with polynomials, we can talk about local maximums and local minimums unless we restrict the domain. Only look at a certain set of values. Only look at a certain neighborhood, and then we can have a global maximum or a global minimum. With constraint optimization, we do a similar kind of thing to restricting the domain. And we'll want to do something like this. Find, let's just do the one I always do. Find the dimensions of a cylinder (282 below). It is below sea level. Awesome. That's the thing I was worried about. I hit that point in my Wikipedia, the Wikipedia section of my brain, and I found that to be empty. I'm like, oh, hey, I knew this at one point. It's like stuff just kind of randomly disappears. It's really ridiculous. Now, if we just look at this statement don't make any sense. Find the dimensions of a closed cylinder with minimum surface area. That's not enough. Because I'll just make a cylinder with surface area of 0 by not building a cylinder. So we want to put some kind of constraint on this. Our objective is to minimize the surface area, but it should be subject to some constraints. We have to contain a certain amount of, let's say, carbonated beverage, carbonated sugar water, like soda. So find the dimensions of a closed cylinder with a volume of, let's say, 250 milliliters. I'll just make it smaller. I wrote 250 wrong, so I'll just go 200. Marketing will take it up with me later. Let's find the dimensions of a closed cylinder with a volume of 200 milliliters that has a minimum surface area. Now I realize that this is not how we build cans, because this is going to make a can that's as close as possible to a sphere. If you want to be efficient with your surface area, make a sphere. It's really hard to make a sphere though, like out of a hunk of metal. And it's really inconvenient to pack. And if it's just a straight cylinder with like angles at the bottom, all the soda would bust out of the cans instantly. So I recognize this is not how we make cans. This is why applications in math class are so dumb. Because it's like they never represent how we actually do things. Everybody remember the one where a farmer is going to build a pen, and he's got to put 3 sides up against a river. Like, who the hell is building a pen up against a river? That was always my problem with the problem. It's like, oh, why is he putting a fence next to the river? And it's like, oh, because he wants to put the sheep in there. So he wants to drown his sheep when it rains? Is that what you're telling me? This farmer seems like a sadist. My teacher used to my bullshit. You're like, all right, he's gonna build it up against the barn. I'm like, all right, that kind of makes sense. Because then you can put a door in the barn and the sheep can go inside when it's raining and not drown when it rains. Anyway. Point was, it was a bullshit question. Here's another fun fact growing up in the 70s. Fun fact growing up in the 70s. So like when there's a word problem, it's like, oh, Arthur, Bob, and Charlie. And everybody's like, oh, hey, this is America and everything is racist. It's like, all right, we'll fix that. Arthur, Jose, and Sheila. And then it's like, oh, there, fixed. Racism over in math class. And I go, that didn't do, but it was like the 70s. Anyway. Or the even better fix. Arthur, Bob, and Denzel. It's like, oh, what did you do? And then they're like, oh, well, we made one of the names. Oh. It's like, yeah, that was worse, wasn't it? Yeah, seriously, why do they have to have names? Like, did you ever see your own name in a math book and think, ah, now this problem makes more sense to me. I feel a connection. That's representation. We don't.
There's like, oh, there's a student name with a question that we're going over the text. That's fine.
See, then there's like an actual personal connection, but I never saw my name in a math book and felt like more connected. Like if we see a person in a movie that's like you, that's good representation, right? Oh, look, this superhero looks like me. I realize that from purely physical appearances, all superheroes, most superheroes look like me, but that's beside the point. It's like, that doesn't fix things in math. I mean, because the school is still racist. But anyway, that's all beside the point. Don't worry about, this is not how we actually build cans. Cans are only vaguely cylinders. We have a fixed volume and we want to minimize the surface area. We have some objective and a constraint. Here's our objective. And here is a constraint. From a school standpoint, we want to maximize the pass rate. All right, everybody will pass. So, and subject to the constraint that students still know some of the information from the class. And we want this to have, but we want to adapt this to now a function of two variables. So we boil all this down to this problem. We want to optimize f of xy subject to g of xy equals k. That's our constraint. Optimize a function subject to some constraints. And we want to describe both of them. We want to describe both of them with a function of two variables rather than just a function of one variable. So this is going to be our project from next week because I couldn't stay on point today, which is typical for the last day of the week. Any questions? Comments? Snide remarks? No, not informative. Click on 3 times speed. All right, that's going to do it for today. That's going to do it for this week. I'll see y'all on Tuesday. Everybody have a nice long 4-day weekend. And thanks for playing.
Peace out, Professor.